Just a second. We need to turn on the recording. Oh, okay.
Ready.
Our next talk is by Nikita Nekrasov, exact computations in non-supersymmetric theories using localization 30 years later.
Okay, so let me try to...
Control L will make your presentation bigger.
Even bigger? Let's see.
Control and L.
No.
No, I already did that.
Maybe Command and L.
On Apple it doesn't work. Control.
No, it worked, but I did it beforehand.
Remove these bookmarks.
So how do I remove this zoom
Press the
cross?
Bookmarks.
Мне кажется, нужно нажать на Tools, и там будет какой-нибудь full screen.
Так это that's what I did.
Маленькие стрелочки по бокам поля. Вот их маленькие стрелочки по центру, по бокам, на боковых границах.
Так.
Вот маленькие стрелочки. Вот.
У меня нету их.
Ну как-то нет.
Command L сработает.
Слева у тебя bookmark есть?
Нет.
А у нас есть.
Obviously, we're seeing different screens.
Да, так ты там нажми правильный экран. Там
что у тебя написано?
Можно переделать заново шеринг.
Okay.
Вот и шеришь iPad или компьютер.
Your screen sharing is it's computer. Okay, let me stop the share and then.
А ты расширь, да, этот самый акробат, тогда будет.
Так, вот я его и расширил.
О, замечательно.
Okay, so I just repeated the same operation. Okay, sorry for it's only appropriate for a birthday conference to do things that only old people do, not being able to turn on the presentation. So it's my pleasure to give a talk in honor of Nikita and Lyonya. We share many things. There are two obvious things which we share with both honorees, and there are less obvious things. So I'm going to talk about the less obvious things. So it's a common misconception that exact computations in quantum field theory, which are done using what is now called supersymmetric localization, only compute boring quantities like Wheaton index, the differences of the numbers of bosonic and fermionic vacua, or some topological invariants. In fact, 30 years ago, Wheaton showed how one can interpret the exact solution of dimensional Young-Mills theory, which was obtained actually 10 years earlier by Sasha Migdal. So on the one hand, this exact computation can be done by triangulating Riemann surface, writing what people at the time were proposing for the lattice regularization of QCD as an alternative of Wilson-Plaquette action. So that was like a group-like version of the Villain action. And Migdal showed that in 2 dimensions, that approximation is actually exact. You can pass from fine triangulation to more coarse triangulation by integrating out the group variables associated to edges and obtain the exact partition function. So Wheaton showed that you can actually resum this expression by a kind of possible resummation and obtain the result in the form of which exactly corresponds to what you would get from kind of a localization computation So there would be a contribution from the modular space of flat connections on the Riemann surface on which you study Young-Mills theory, which has actually topological meaning, and it explains the finiteness of the perturbation theory in that theory. And then there are some non-perturbative corrections which are also exactly computable. So Witten actually attributed it to some kind of Dyson-Macdonald formula. He called it non-abelian localization, and it was hailed as a new type of localization, which in fact was not a new type. It's essentially the Dyson-Macdonald with additional Fourier transform. But the main point was that he explained this by embedding the bosonic theory, so theory without supersymmetry, by adding to it a kind of a system of non-dynamical fermions, the action involving just essentially the mass term for additional fermionic degrees of freedom, and he embedded it as a subsector of the supersymmetric Young-Mills theory, to which one can apply the previously developed techniques of exact computations. So in that way, the states of the original Young-Mills theory, which are bosonic states in the theory without supersymmetry, turns out to be the vacua, supersymmetric vacua of an enlarged theory. And that embedding, even so it might seem excessive, actually is useful because you can find it another representation of the path integral in supersymmetric theory, which admits the exact evaluation. So in this way, one can compute many interesting things, and in particular, the computation of the heat kernel on compact group manifolds, which were of course done by mathematicians, over 100 years previously, get a kind of a new interpretation in terms of the localization on the loop group, and so that's useful, and it's being discussed to this day, as you will probably see in Leon Dr. Jan's talk, if you haven't seen it already. I'm sorry, I don't remember the order of presentations. Now, a closely related problem to the geodesics on the group, I mean, or harmonic analysis on group manifold, is that of the quantum mechanics of the Calogero-Moser system, which in the case of the A-root system, so that system, of course, has the analogs for any root systems, as was demonstrated by Olshanevsky and Perelomov. I mean, it was demonstrated that it's integrable. But for the A-type, it can be found, that system can be found within the two-dimensional Young-Mills theory with additional Wilson loops, Wilson line. Although, if you are honest about it, then the two-dimensional Young-Mills theory with the Wilson lines in the representations which are admissible in gauge theory with compact gauge group would only correspond to special values of the coupling constant. So the coupling constant here, the parameter nu has to be integer. And then using this Witten's embedding of 2D Young-Mills into supersymmetric theory, you can, and the fact that that theory is actually two-dimensional, you can both understand why it is integrable, why this quantum mechanical system is integrable, and one can use the tricks of two-dimensional field theory to compute the spectrum and wave functions. Even though this problem starts as non-supersymmetric, but you embed it in the enhanced theory with supersymmetry and do some manipulations which allow you to compute things. So together with Sasha Gorsky, again, 30 years ago, we asked whether one can use supersymmetry and exact computations, which at that time were not that abundant, to produce exact results and maybe compute wave functions of at least integrable quantum mechanical systems and maybe quantum field theories. So it turned in 30 years which passed, many people, and I including me, found that by choosing the appropriate gauge theory, and sometimes you have to go high in dimensions, you will find that many interesting topics in mathematical physics, ranging from hyperbolic geometry, beta and Zatz beta equations, isomorphic deformations, invariance of manifolds. I just listed a few. Are connected to these techniques, and so that's obviously bears a lot of connections to the works of Leon and Nikita, and that's why I thought it would be an appropriate topic for today's talk. So going back to this question of Calogero systems, if you really try to include the non-integer coupling constants into the problem, it requires, well, kind of a paradigm shift, because in order to admit non-quantized values of the coupling constant, you must have a modification of gauge theory, where in some regions of space-time the gauge group is compact, and in some regions of space-time, including those where the Wilson line, which is the source of this additional interaction, the gauge group is probably non-compact. So because non-compact groups admit continuous principal series or complementary series representations, which are parameterized by continuous values of the spin. So it's a novel type of gauge theory. I mean, 30 years ago, we did not know about these theories, but nowadays we understand them as boundary phases of topological theories or partially topological theories which live in higher dimensions. And okay, well, 30 years ago, we knew about the connection between, let's say, conformal field theories in 2 dimensions and Chern-Simons, or more generally, topological field theories in 3 dimensions. But that still required special values of various parameters, like level of the current algebra or central charge of Virasoro algebra. But now we understand that these requirements can be relaxed at the expense of promoting the 3-dimensional bulk theory to be, in turn, a boundary of a high-dimensional theory, 4-dimensional, n equals 4 superangles, for example. Well, it turns out that in order to understand the Calogero-Moser system for generic values of the coupling constants and many other interesting systems, which I will mention today, one should go to 4-dimensional n equals 2 gauge theories. So in Witten's example, he started with theory with 0 supersymmetry and embedded it into the theory with 4 supercharges. It was n equals 2 Young-Mills in 2 dimensions. And we are now going to double both the number of space-time dimensions and number of supercharges. So n equals 2 in 4 dimensions is 8 supercharges, 8 supersymmetries. Now you could generalize this question and ask about more general situation where one has a problem where there are some parameters which are naturally integers, and then try to analytically continue them to complex values. And that's what's been done in quantum field theory and statistical mechanics for ages now. So let me just mention 3 famous examples of such tricks. Regge analysis, which interprets the particles as poles in S matrix, analytically continued in angular momentum. Replica trick in the theory of disordered systems and spin glasses, where you have some statistical mechanical model which depends on random have some coupling constants, for example, Ising model with the random spin-spin interaction, and the physics of the model requires you averaging the free energy with respect to those parameters, which is hard. So instead, you average the powers of the partition function of the original system by basically introducing several copies of your original degrees of freedom, several replicas, and then you do the analytic continuation in the number of copies in this parameter n. And of course, the dimensional regularization, which is used, for example, in proving that the Weinberg-Salam theory is renormalizable. So where you take the space-time dimension and make it a complex number, and then study the analytic properties of Feynman diagrams as functions of space-time dimension. So in all these examples, you take something which is naturally integral and then make it complex. So the question which I want to ask is there any physical meaning to these complexifications? Namely, is there a physical system which would realize complex spin representations of, let's say, group SLN, so SL2 being the Lorentz group in 4 dimensions, which physical system partition function is a complex power of the partition function of the original system? And the related question, actually, using the Walsh-Sheet approach, is to make the space-time dimension, which is a central charge of the matrix sector of the Walsh-Sheet theory, to be complex. So what's the physical realization of Virasoro representations with complex central charge? So by physical realization, I mean a quantum field theory, which at least for some values of parameters has a standard Hermitian Hamiltonian, has a Hilbert space, and there is a subspace in the Hilbert space, some subsector in the space of observables, which will look like the much smaller physical system with complexified number of replicas, space-time dimensions, or spin. So I will argue that it is possible, but you basically embed your original model into high-dimensional model with some supersymmetry. Supersymmetry would essentially cancel the contributions of bosons and fermions in the bulk of this extra-dimensional theory, so that for a restricted set of observables, the theory would look like the lower dimensional theory with fewer or no supersymmetry. But the lack of cancellations close to the boundary would be responsible for this weird complex exponents or complex spins. So let me start with something simple. Let's talk about representation theory of the group of the algebra SL2. So you can realize the SL2 algebra in tensors in living in 1 dimension. If the spin S is half integer, then there is a fine dimensional representation, which is a representation of the group. So when 2S is an integer, this expression makes sense. And in this case, we can understand this as a quantization of a 2-dimensional sphere with the symplectic form, which is the volume form on the sphere times the spin. And so the wave functions in this case will be globally defined over the sphere as holomorphic sections of some line bundle. But once the spin becomes complex, these differential operators which I use still make sense. The group action is lost, but the algebra action makes sense, and you can make various restrictions on the nature of this coefficient functions psi, and get various representations like Fermat modules where you have polynomials, or Heisenberg-Weil modules which have a form of some complex power of the variable x times a polynomial in Laurent polynomial in x. So you might find this representation slightly unfamiliar. So we all know about Fermat modules, but these HW modules are maybe less known. For you encounter them in the representation theory of non-compact groups for special values of S and A. They are called, you find them in principal series and in complementary series of SL2R representations, and also the so-called Harishchandra modules. But in general, they don't integrate the representations of the group. Now, if you try to define an invariant in the tensor product of three such representations, so if you just think about functions of X, so you look for the function of three variables x1, x2, x3, which is invariant under the, which is annihilated by the sum of three SL2 generators. That's the only solution to these equations. And then you can interpret this solution as the element of the tensor product of some representations in x1, x2, x3. And so interestingly, that depending on which region of the X space you expand, you'll have different interpretation of this object as the invariant in the tensor product. For example, in the region when x1 is much smaller than x2 than x3, that's a product of Verma with spin s1, HW with spin s2 with a shift s1 minus s3, and co-Verma with spin s3. Now, you can continue this formal analysis by taking the tensor product of many copies of these representations. From this three-point example, you learned that you basically need two Verma modules and then fill the rest with these HW modules. And you can write a famous system of using the logic of equations, which are compatible equations on the function psi of two sets of variables. So the variables z and the variables x. So the variables x are where the SL2 is realized, and the variables z correspond in the language of conformal field theory the positions of insertions of vertex operators. But we don't have yet the CFT because this we're just talking about the SL2C representation theory. So if the spins are again half integers, one can.
Nikita, sorry, may I just, so what is X again, Xi?
So Xi's are
Xij are differences. That's
yes. So psi is a function of variables z0, z1, zn plus 1, and x0, x1, xn plus 1. So they're complex numbers. So they live maybe in some domain of CP1, and we are looking for the function which solves these equations, that the z derivative is equivalent to the action of this operator hi.
Mm-hmm. Thank you.
So you can think of it as some kind of a quantum top where the spin variables are now continuous. So it's a generalization of the well-known problem where if 2s is an integer, then you can restrict psi to be a polynomial in X of degree 2s. So you need 2s to be an integer to say that it's a degree. And then essentially, since it's a polynomial has a finite number of parameters, you can view them as vectors in some just tensor product of vector spaces, finite dimensional vector spaces. And so then these are just now differential matrix equations, which are of course the equation of conformal blocks of SU2 assuming the Novikov-Wheaton theory at level K, where the right-hand side coincides with Godet Hamiltonians. So these equations, of course, were studied by mathematicians and physicists for generic K, and K is continuing to view the level K as a parameter. So the question is, what is the physics which would produce these functions for generic K and generic S also? Now, another story of that type is the generalization of Dyson-Macdonald identities, where so that's probably 80 years old, where so both Freeman Dyson and in Macdonald discovered that certain powers of the Dirichlet eta function have nice Q expansions. There's a nice story about this, but which I don't have time to go there. So, and it has some nowadays interpretation again in terms of the CFT of, let's say, WZW type based on the group G. Now, not so long ago, it was discovered that there is some systematics in the expansions of complex powers of the Dirichlet eta function. In fact, so if you can represent the exponent in the form which uses 3 parameters, so it's not unique. There are many ways to do that. But in particular, if epsilon1 is equal to minus epsilon2 and m over epsilon is an integer, then that would be a dimension of the group SUN. And so that will be a particular case of Dyson-Macdonald formula. This power expands as a sum of Young diagrams with a relatively simple weight of the diagram having to do with the shape of Young diagram. So you need to know for each square in a diagram its arm length and its leg length. So it's some rational function which is not so difficult to compute. It generalizes the Hooke formula for the dimensions of the representation of symmetric group. So in line of these questions about replicas, you might say that if you take a system of if you take a chiral boson, 2-dimensional chiral boson, and take its replica, so you take a complex number of chiral bosons, its partition function actually has a has an expansion which it's not yet an expansion of a partition function of a physical system because these coefficients are complex, but this quantity can be Q deformed. Sorry, probably in the next slide. And then it will become actually the trace of the, so this is called refinement. It will be actually become a character of some vector space, which is actually, it's a super vector space. So the rule of the game is that every time you see this at the denominator, you can make it into 1 minus Q1 time to the power a plus 1 Q2 to the power minus L. So that can be expanded in geometric series, and that would be a contribution of some bosonic degree of freedom. Every time you see the numerator, you write it as 1 minus exponential of that, and that would be a contribution. So this quantity actually is a limit of a super trace of some system of bosons and fermions with chemical potentials corresponding to certain symmetries. So the refinement of that formula is actually a partition function, supersymmetric partition function of a reasonable physics system. So what the system is, it's the so-called, well, it turns out to be 6-dimensional. So it's a 6-dimensional tensor multiplet with 2,0 supersymmetry, which lives in the geometry of which is a product of a 2 torus, where the original chiral boson lived, times the 4-dimensional space. So this is the alternative to the use of the Lin category, which is interpolating category of representations of general linear groups or orthogonal symplectic groups to the complex number of colors. In that we deal with the actual spaces of states of more or less conventional quantum field theory, although in this example it's chiral. So this tensor theory is famous for being the high-dimensional analog of the chiral boson. So it's a theory with well-defined Hamiltonian, but without a nice Lagrangian. So in this way, one can ask about other systems, and I'll just mention that an interesting example is the three-dimensional conformally coupled scalar. So you take a free boson in 3 dimensions, you define it in such a way that even on curved manifolds, it has a conformal invariance. So it means that it has a mass which depends on the curvature of spacetime. And then it turns out that if you take it on the geometry of the product of 2 spheres and a circle, so it's like a 3-dimensional analog of a torus, its partition function is equal to the Mach-Machen function, the sum of 3-dimensional over plane partitions, and its replica, that is to say, the complex power of that partition function, can be again given the physical interpretation as a supersymmetric partition function of a higher-dimensional theory, and that theory turns out to be the 11-dimensional linearized supergravity. So, so these realizations of replicas by physical systems come at a cost. They require you going to higher dimensions, but they exist, and so that's an interesting lesson of this exercise. Okay, so how much time do I have?
You have about 10 minutes.
10 more minutes. Okay, so I'll need to be very, very brief. So my next example, which brings back to this many-body systems and connections to Calogero Moser and other models, will use the 4-dimensional gauge theory with n equals to supersymmetry. And my basic example would be the simplest type of such theory in the AD classification has type A1. It's the UN theory with 2n fundamental hypermultiplets. It has various realizations, de Bruijn realizations, so on and so forth. Quite a few things can be computed. The supersymmetric partition function is given by the sum over collections of Young diagrams. So it's a slight generalization of the formula I had earlier for the powers of Dedekind function. So here, so there are, let me just list the parameters of this partition function. There are n complex parameters, which are called Coulomb moduli. There are 2 n complex parameters, which are the masses of hypermultiplets. There is a fugacity for the instantons. In the sum over partitions of Young diagrams, it weighs the sizes of partitions. And so in the limit when, yes, sorry, and there are 2 main parameters, which are the parameters of omega deformation. I will not explain what it is. So there are 2 complex numbers, epsilon 1 and epsilon 2. In the limit when they are set to 0, this partition function has the limit shape asymptotics, where it reveals the connection to an algebraic integrable system, the classical Godin system on a sphere with 4 punctures, where so there's a spectral curve, which is the spectral curve over meromorphic matrix, which has 4 poles. In this case, it has 4 poles of the sphere at points 0, q1, and infinity. Q was the fugacity for the instanton counting. And the eigenvalues of the residues of this meromorphic Higgs field are related to the masses. So you split 2n masses into 2 groups of n. And so the residue at 0 has n distinct eigenvalues. The residue at infinity has the other set of n distinct eigenvalues. And the residues at q and 1 have maximally degenerate eigenvalues. So that curve sits in the cotangent bundle to P1. There is a canonical differential. You compute the periods of that differential over cycles on that curve. They're related by special geometry relations, and that gives you prepotential F, which is the leading asymptotics of that partition function. Now, that was a classical integrable system. If you go back to the doubly deformed system with epsilon 1 and epsilon 2, you actually get the quantum version of the asymptotic deformation problem, which was shown by Reshetikhin, is actually a Knirgner-Molodchikov equation. And starting, I believe, with given tile, it was observed that the same type of equations are found in instanton counting in two-dimensional single models. It's quantum differential equation. Famously, it has two quasi-classical limits. One when the coefficient in front of the derivative goes to 0, and that's corresponds to the let's say quantum Gaden system, and another when it goes to infinity, where you get the isomonodromic deformation problem, classical isomonodromic deformation problem. So the objects which you need to study, it turns out, to reveal those integrable systems and isomonodromic systems are called the surface defects. So these are four-dimensional gauge theories with additional singularity along the two-dimensional surface. And after some work, which took actually, I would say, 20-some years, it was shown, well, we published it last year, but we found it in 2017 with Sasha Cymbaluk, that the equation that the surface defect solves is isomorphic to the 4-point Nijinski-Molodchev equation of the type I start with for the group SLN, for the Lie algebra SLN, sorry, with complex spins. So the spins associated to the positions of vertex operators 0, Q1, and infinity are related to the masses in a way similar to the residues of the Higgs field, and they are complex, so they correspond to infinite dimensional representations. So the presentations are the ones which I mentioned earlier. For SL2, there are SLN analogs of that. So there is a Fermat module at 0, there is a dual Fermat module at infinity, dual in the sense that one is lowest weight, another is highest weight, and then there are these unbounded modules of Heisenberg and Weil at the intermediate points. So in various limits, which have the physical meaning in these gauge theories as limits when you recover Poincare invariance, super Poincare invariance in some of the dimensions, you will get as limits the isomonodromic tau functions or wave functions of certain quantum integrable system, which I will go to later. But the interesting point is that if you try to interpret this conformal block, so the solution of this equation as a conformal block of some kind of WZW theory with analytically continued spins and levels, and then try to interpret that in turn as a wave function of Chern-Simons theory, living on maybe a three-dimensional ball whose boundary is the sphere with 4 punctures, which are the endpoints of some line operators, you cannot, because the spins are complex. You cannot write an observable in three-dimensional Chern-Simons theory, which would represent the representation of the Lie algebra and not the representation of the group. So after some deliberation, you find that this line, which you naively would start at the surface and send inside the three-dimensional bulk, is actually a boundary of a surface which goes into 4-dimensional bulk. So it's a counterexample to the boundary of the boundary being 0. This, you need to consider manifolds, 4 manifolds with corners, such that the boundary contains this 2-dimensional surface sphere. So the answer is that this is not a 3-dimensional Chern-Simons theory. It's a 4-dimensional n equals 4 super-Yang-Mills theory, which is different from the n equals 2 theory I start with. So there are 2 4-dimensional theories behind this analytic continuation of WZW conformal blocks, and these 2 4-dimensional theories, they sit inside the same 6-dimensional theory, which I will now skip. This is not an accident. So this story is just the tip of the iceberg. You can add additional surface defects in 4 dimensions in n equals 2 4-dimensional theory, and you can that will insert additional vertex operators on the Nijinski-Molodchev side. One option is to consider intersecting surface defects which intersect transversely. That would give the vertex operator corresponding to a finite dimensional representation. But interestingly, recently we found with my former students, Semyon Jong and Norton Lee, that by adding a parallel canonical surface defect, you will find novel type of vertex apparatus in WZW theory with complex values of the level, which correspond to so-called twisted chiral vacuum modules, which define the extension to the non-critical level of Hecke modifications studied by Behrens and Greenfield, and recently for n equals 2 studied by Ettingov, Frank, and Kashdan in the context of analytical and lens correspondence. Now, so there is some use to this high dimensional perspective, even in the case when the original model had a purely two-dimensional interpretation. Let me just mention the application to the isomonodromy problem by doing a certain standard game in four-dimensional gauge theory when you compare the theory on blown up spaces, when you insert a two-sphere of small size and compare partition functions, you get the identities which are completely crazy from the two-dimensional point of view, the identities which change the parameters epsilon, which determine the levels of the current algebra of central charges of Virasoro. And that way you get an understanding of the origin of the Gamayun, Yorgov, Lissovy Kiev formula from 10 years ago in the limit, and you get an extension of that. So going back to the Calogero-Moser system, it's a surface defect in the n equals to 2 star theory, which is a theory with hypermultiplet and adjoint representation. So there is an explicit formula for the surface defect of that theory, and it was proven rigorously that it solves the elliptic version of Knizhni-Molodchikov equation, Knizhni-Molodchikov Bernard equation. It remains to take a limit epsilon 2 to 0, so the critical level limit, to produce the eigenfunction of the elliptical Calogero-Moser system. It is still complicated, unfortunately, but there are some simple versions. So one is the hyperbolic version, which is simple, and that way you get the explicit formulas for the wave functions of hyperbolic Calogero-Moser system with the Coulomb parameters A playing the role of the symptotic momenta. So you can compare this to the talk of Serozha. And another limit, which is well known to the periodic Toda system, when you take simultaneously the generate elliptic curve and send the mass to infinity, that gives you periodic Toda, and that can be undeformed back to the A1 type system, which I discussed, the theory with fundamental hypermultiplets. And in that case, taking the epsilon 2 0 limit is doable. So that will give you the eigenfunction of the genus 0 Godin model. It is also an n particle system, which now depends on 2n parameters. So it's a kind of a deformation of the periodic Toda chain. And in that case, the surface defect partition function gives you a formula for the wave function, which generalizes the integral formulas of Kirchhoff and Levitin. So I would like to conclude with wishing happy birthday to Leonia and Nikita, and the pictures of high dimensional partitions, which I drew here, hint at many more surprises in quantum geometry integrability, which we will get by considering high dimensional models of versions of the models I discussed. Some of them include quantum dynamics. Thank you very much.
Thank you very much. Thank you very much. Any questions or comments?
Of course, I have many questions. I will not ask all of them. Just maybe a couple. Thank you, Nikita, for this illuminating talk. It has so many facets that I think audience is a little bit lost.
Sorry about it.
But I just just want to make some small considering the small part of this activity, because what what is now called Nekrasov partition functions. They are closely related to Liouville theory.
So, what I discussed here, because it was this general N, I had this general N. So this is it's believed to be the conformal block of the Toda conformal Toda system. So for n equals 2, it's Liouville. Yes. So this formula. Sorry, what was the formula? Yes. So this is the formula for the conformal block of an minus 1 Toda on a sphere with 4 punctures with the 2 regular punctures and 2 minimal punctures.
So it's really related to Liouville theory, right? That's what.
For n equals 2, it is exactly the conformal block of Liouville, because for n equals 2 there is no distinction between minimal and regular punctures. Yes. So that was shown by more or less explicit computation that with Shapovalov formed it conformal block.
But for higher n, because we are basically interested in large n.
But for high rank, it's not Liouville. No. For high rank, it's a WN algebra, which is hiding here.
And special fields.
And special fields, right? As I said, regular and minimal. Yes, if you, unlike Liouville for higher n, even for Liouville, it's what is simple in 4-dimensional gauge theory only corresponds to a special channel in Liouville. So if you want to get a conformal block in the general channel, it's unfortunately we're still slow in developing instanton calculus for those systems, for those channels. But it's going to be too technical.
Okay, but anyway, it's possibly discussion, not a question.
Yeah. Yes. I mean, so what I described is an attempt to understand this, to derive this relation without, highbrow mathematics, because maybe what I should mention is that the proof that not this partition function, but this associate partition function with the, where was it? Surface defect with the Zian structure. Yes, this one. So it's a slight modification of the partition function. The fact that it solves the KZ equation, essentially, it's a cumbersome calculation, but it's essentially an elementary calculation. You don't need to know, the university mathematics standard. Well, you need to know residues. and the rest is just the consequence of that.
Yes, I wish my students would know residues. Okay.
Well, that's useful. It's it's the same residues as used in. It turns out it's the same residues as used in the functional beta ansatz. So that's why I like this.
It just it's not a question. It's just a small remark that we actually try to relate this to this topological recursion of quantum curves.
Right. So that's an interesting question indeed. And strictly speaking, topological recursion corresponds to the case epsilon 1 equals minus epsilon 2. There are some claims by Inar that he can do the general case when epsilon 1 is not equal to minus epsilon 2.
No, it's not. It's actually by us, by Inar, myself, and
yes. Okay. So I when I say claim by Inar, it means that I had a conversation with him at the Blackboard.
No, but
maybe it was a long time ago.
We actually have 2 papers.
You have 2 papers, right? Sorry. I forgot. Right. So I don't understand, unfortunately, it at the conceptual level, but I think it's true, and it would be nice to relate the the kind of microscopics of the equations which I use, which are these non-perturbative Dyson-Schwinger equations, which modify Young diagram by adding or removing one box, to the essentially loop equations which you use in topological recursion.
But it's not a standard topological recursion. It's something weird. It's topological recursion on quantum curves. So it's,
well, that I don't like. That.
well, but that's life. So it's we have to live with it somehow.
Okay.
No, recursion is with respect to the product. Epsilon1, epsilon2 is 1 over n square.
Yes, yes.
But all the rest basically arbitrary.
Right. But so what is the quantization parameter? Is epsilon1 plus epsilon2 for you?
Some combination. No, it's a difference. Actually, they're different. So in classical case is classical. So this combination is 0 and h bar is 0.
Okay. Well, I don't know, but I think it's a good it's a very respectable problem to understand the relation between the topological recursion or its beta deformed version and this.
Beta is again, it's in some regime. So beta is semi-classical.
By beta I mean epsilon1 plus epsilon2 being non-zero.
Yes. So it's a bit, but if it is small, it's just semi-classical.
Okay.
But interesting question, I think, is when it's not small.
So the question is whether. So what is the curve that you start with? Is this? So here I drew the brain picture. It's a tropical limit of the curve. So that curve is a spectral curve for Godin, which is the n-fold cover of the sphere with punctures. Is that the curve for which you use the recursion, or it's something else? It can be quantized.
It's hard to relate these two. Well, these two languages.
Quantization is the TQ equation of this Godin system. So there is a good. Remember, I said towards the end that there is this. So there's
I like the picture. I like it. It's actually, again, it's very much resembles what we have. So we have some monodromies of quantum Liouville system.
Liouville for n equals 2 or in general.
I hopefully think it's for general.
It's 4 points, but n is general. So it's 4 points with high rank. Yeah. Well, anyway, okay. Okay, good.
Okay, but anyway, so I would like to discuss it one day. I don't know where you are.
Well, I'm on Zoom. So.
On Zoom, well, it's somewhere in the cloud.
Yeah, that's right.
No, but we have to. I'm sorry.
I think we should discuss.
We should stop.
I just since it's a birthday conference. I think every 10 years or so, when we meet, we also meet sometimes with Tolstoy. So we say that.
Yeah, sure. And I'm sorry for torturing you, but I have rights of the groom on this conference. So
of course. But okay, let me stop sharing.
Did I hear groom?
Yes.
Yeah.
Actually, I have a blackboard, so I can write something on the blackboard. Maybe it's not visible.